Everyone, and welcome to activity 4. Today we are going to talk about using our exponentials to solve some real life problems. So when we have our exponentials, think this is the format of our geometrics, right? If we're connecting it to our previous units, we had our geometric sequences, our explicit formula that we're growing exponentially. And these are important because our variable is in the exponent. And that's what makes this so special. So again, we see this function that's basically showing us a times b to the x power is kind of our format here. And again, that mimics for us from the last unit geometric explicit formulas. Now notice all of these graphs, all of these exponentials, 10 to the x, 3 to the x, 2 to the x, they all have this same point at 0, 1. And why is that? Well, anything to the 0 power is 1. So that's why they're all going to share that same point, 0, 1, because anything to the x power of 0 will just make that value 1. And again, our exponential function is a quantity representing the power to which the base must be raised. And again, that's what we see in this graph here. Okay, now our applications then can vary, but oftentimes we use the most basic way with growth and decay problems. So to find our amount, we start with a principal starting value, our initial amount. And then for growth, we take 1 plus an r value to the t. And then for a decay, we would subtract. So think about like 1 is representing 100%, right? And if we are growing something, we are retaining 100% plus something. If we are decaying, it would be the 100% minus. So that's where those R values are coming in handy because anything less than 1 would cause our exponential to decrease. Anything greater, we are increasing. And again, the t value then is our time, usually in years, may depend on the example. So for some of our examples here, we are finding our amount value using the given info. So the first one says we have a company that promises to release a new smartphone every year. Each model's battery life will be 6.1% longer than the previous models. If the current battery is 745 minutes, what is the latest model battery life 19 months from now? So be careful because we were initially talking years, they gave us months, right? Well, 19 months, if we divide that by how many months are in a year, it's really 1.583 years on this one, right? 1.583 repeating. So we're going to kind of have to make that conversion on this since our initial part was talking about years. And then to find the amount of battery life we have, if we initially are starting at 745 minutes and we are adding on 6.1% to this over the course of our 1.583 repeating years. So we're going to add in a couple extra threes just to make sure we get good rounding. Now, reminder when it comes to writing this in, they will give us our value as a percent. When we plug this in as an R value, we have to move our decimal point back. So that's why our R value becomes 0.061. So just a side note for that. Now, our next piece then is just type this in the calculator. So our initial principal value, 1 plus 0.061 to our t power, so 1.583, repeating. Can throw a couple extra on there. And it is going to have about 818.22 minutes of battery life in that time. Now our next example is that of a decay, because in our next example it says a car rental company assumes that their fleet depreciates by 6.4% per year, and we want to know after 5 years how much would a car be worth. Okay, so again, we're depreciating. And again, our rate, we have to move that decimal point back 2 spots, so it becomes 0.064 is our R value. So the amount, again, we're going to take that starting principal value, and then since this is depreciating, we're going to subtract away that rate, and then this time we are checking out after 5 years. So we have 39,100, and then 1 minus that R value to the T power, and we see that the car will be worth just over 28,000, right? $28,090.28. It doesn't specifically tell you. Normally with money problems, we tend to round to 2 decimal places. Sometimes it'll say like nearest whole number, but otherwise money goes to the nearest cent. Now our next part is asking us to work backwards to find the time value on the problem. So notice in this one it says in 1995 we had 85 rabbits in Central Park. So our starting was 85, and then our population increased by 12%. So 0.12 this time, because again, we're going to move that back 2 spots. And we want to know how long before there are 990 rabbits in Central Park and how many were there in 2011. So let's start with the 990. We want to basically see when is our amount 990 when we started with 85. And again, this time our population was increasing, so there's that growth. And we're solving for the T value. So to kick this thing off, we're going to divide the 85 over. So we're going to take 990 and we are going to divide away the 85. Oops, not 9,000. 990 divided by the 85. And we see that that's giving us about 11.6705. And on these problems, you really want to make sure you are using a lot of decimal places to get the most accurate answer possible on this. And then we have 1 plus 0.12, so 1.12 to the T power. Now to undo this basic piece here, we're going to actually go back to our properties of what we call our logarithms. Logarithms, which we'll talk more about in the next activity, undo our exponentials, because if we take the common log of both sides, what this allows us to do is move our T value out front. It's no longer going to be an exponent. So what that would look like is the log of our 11.647. Again, use more decimal places than even that, saving a little space. The T now is out front, and we have the log of 1.12. Now, log is a button on your calculator, right? We see that right here is our common log button on the left-hand side. And to get T by ourselves, we can take the log of 11.647 and all those other decimal places and divide it by that log of 1.12, right? Because that'll cancel out and get T by itself. So if we take our log of the 11, again, we want to use lots of decimal places, so I'm going to plug that in, divided by the log of 1.12, we get our final answer that it's going to take about 21.66 years for this to happen. Now, the other part of this was kind of similar to the last part, is how many rabbits are there in 2011? Well, 2011 is going to be 16 years after our initial year of 1995, right? We had 16 years. So plugging in then to figure out our amount of rabbits in that year, we're just going back to what we did before, taking our initial population, then the 1 plus the 0.12 to the 16th power, and we would notice we would get right around 521 rabbits. All right, now using that same type of problem with some depreciation, in this case we are depreciating by 12%, so this time our rate is 0.12 again, but we're depreciating, so we'll subtract. And we want to know how long is it going to take our car to be worth $5,000. So if we look at that amount, we want it to be $5,000. Again, it started at $17,000 and we're subtracting away this time because it's depreciating. And again, we're going to start, we want to isolate the t as much as possible. So we're going to take the 17,000 and divide it over to get our r to the t kind of by itself. So we get about 0.29411 over here. And use a bunch of different decimal places to keep it very accurate. And then we have 1 minus 0.12, so 0.88 to the t power. Very similar to what we did up above, we need to take the log of both sides because what that will allow us to do is, again, bring that t out front. So to find our t value, we're going to take the log of the 0.29411 and divide over this log of 0.88 so that we have the t by itself. So log of our 0.29, so again that previous answer up above, second negative sign, divided by log of 0.88. We see that it's going to take about 9.573 years. All right, number 5 is for you to try. This time you have a nickel. So think about a nickel's starting worth is just 5 cents. And it is increasing at a rate of 8.149% each year. When is our nickel going to be worth $234? All right, down at the bottom part, our last type is when we are looking for that R value. So we have, for instance, in number 6, that we had a fund that started at $764,000 and it decreased over time to $74,000. And we know that the time was over the course of 7 years. We want to find the R value this time. So we can plug in that information, right? We know we started with $74,000 as our initial amount of money in the account. We went down to $74,000. The initial amount in the account was $764,000. And we know it's depreciating. It's getting smaller, so we know that that R value would be negative. And this is over the course of 17 years. So our goal is to get that R value by itself. So we're going to start, again, we're going to divide over everything by the 764,000. Okay, that's our first step here. We get that the 74,451.53 divided by the 764,000 gives us about 0.097. Again, you're going to want to use a couple decimal places beyond that to get a good read. And right now that equals 1 minus our R to the 17th power. Well, just like last unit, if we want to get that parentheses by itself and undo that 17th power, we can 17th root to get rid of that. So again, we're going to just type 17 in our calculator's math button, option 5 to get the 17th root, and we're going to plug in that answer then to take that 17th root, and we get about 0.8720 as our answer there so far. Now this still equals 1 minus our R value. So if we subtract over the 1, right now we have negative 0.127. Go up here. And right now this equals our negative r. The negatives cancel out, and we see that our r is 0.12799. Now, oftentimes they're going to want us to write that as a percent, so that would be, if we move our decimal point back, 12 point, looks like kind of about 8% on that. All right, let's try one more similar to that. Okay, this one this time says we have a social media site that it's increasing consistently a percentage each month. We are growing this time to 52,711 and starting off with 36,720. And again, we want to figure out what is the rate over those 7 months. Now notice this was talking about per month and kept this in months. So this is a per month. Since they're both consistently in months, we don't have to worry about converting on that one. Now, similar to the last problem, we are going to want to start by dividing over our principal amount here so that we get the parentheses as close as possible to by itself. So if we take the 52,711, divide that by that starting amount, 36,720, we get our left-hand side to about 1.43548. Again, you want to use lots of decimal places on this. Now again, at this point, we have the parentheses by themselves, but they're to the 7th power. So we're going to want a 7th root to undo this. So 7, math button, option 5 to 7th root. And I'm going to type in that previous answer. I'm going to just use second negative. You could retype that in. But the 7th root this time is giving us about 1.05299, repeating here. And that's 1 plus r. All right, last but not least, subtract over the 1 this time. And we get 0.05299 as our r value, which, if we move this back, should be about 5.299%, or maybe you just rounded that to 5.3%. They weren't specific on the rounding instructions, so we'll just go to the nearest tenth. All right, thanks everyone for watching these examples. We will definitely be working more with these in class.